You had
acid-base.
acid-base reactions. You had
Bronsted-Lowry.
decomposition, single replacement, combustion, double replacement. Okay? You had all those lists of types of chemical reactions, and what you were responsible for doing was looking at a chemical reaction and saying, oh, that happens to be a combustion. That happens to be a single replacement. And there were rules that followed those reactions. Right? Organic chemistry is very similar. We will have a sequence of types of reactions, and there are rules that follow those types of reactions. They often follow, or they will all follow, different mechanistic steps, allowing you to decide how to go through and process. So what you need to be able to do is recognize a reaction and say, okay, what parts of this are things that I should be looking out for? Does this mean that this is a substitution reaction? Does this mean it's a combustion reaction? So you need to be looking for those cues, those pieces that will tip you off that that's the type of reaction you're doing. Because once you know the type of reaction, you can then do something about predicting the products. If you're just given a bunch of random reactants and you have no idea the type of reaction, how do you predict the product? Well, in Gen Chem, you didn't. You got the question wrong. Same thing's going to happen in organic. What makes organic more difficult is that not only do you have to look at it and say, okay, this is the type of reaction, you now have to go through and do that reaction and explain how and why that reaction is working. And what are the repercussions at each of those steps of the reaction. Right? So what we'll be looking at is try to do an overall picture. These are the types of reactions. These are the pieces to them. These are the things you should be looking for to help you think through it. And then let's look at all the gory nuts and bolts details of each of those individual steps. Okay? Which is actually kind of cool. At least I think it's kind of cool. Okay? We're looking at how to build things. So, if we go back to this, what we're responsible for are curved arrows. We've seen curved arrows before when we looked at resonance. Okay? You take a look at questions 1 and 2 on your exam. I think resonance is really important. This is why I asked almost the identical question 2 times in a row. If you go through and look at your score on those 2 questions, if it is not perfect, we've got some problems. Okay? Because what you're looking at there are the simple, not simple, but the lowest level, if you will, steps behind it, because you're just manipulating what you're already given. When we move into curved arrows and reactions, we have to manipulate a little bit more than that. We have to manipulate, draw a structure, manipulate that structure. Okay? Add more curved arrows, draw a product. Product of that, add more arrows, draw a product. Okay? The issue is you are scaffolding on top of your past answer. If your very first past answer is wrong, everything you do afterwards is wrong. Okay? Which in a show your work, believe it or not, isn't a big deal because I've been overly penalized in situations like that as well. And I will look to see, are you at least doing correct things beyond that one mistake? Okay? Yes, you screwed up the whole process, but I at least understand where you were trying to go and you made one simple mistake. The issue with that is the final exam has no show your work. So you must be able to track consistently correct all the way through. Okay? So, let's start. With all problems, where should you start? At the beginning, which means ignore the end. Okay? We need to transition from the structure on the left to the structure on the right. What changed? Okay, we added a hydrogen, okay, which is a standard kind of interpretation to this because we have a hydrogen shown, and that's a pretty big atom, and that looks like big and fancy. Except what do curved arrows show? The movement of the electrons. So I don't accept that we added a hydrogen. We moved electrons. Better, where did we move electrons to and from? We moved them into a bond. So I took these electrons and I moved them into that bond? Is that a very good arrow? Okay. I'm saying I'm taking electrons and I'm moving them to something that theoretically I made.
Can you move them to the hydrogen on the arrow?
So what we'll have to do is show where those electrons are moving to, and assuming that they will then occupy that space in our product. Okay. So our arrow pushing starts only on the reactants. So I take those electrons and where did I move them to? A hydrogen. Notice where's my arrow starting? The electrons, and it is ending on an atom, yes. On a proton, so all arrows end on protons. Oh, okay. Using the big fancy words there. We're moving the electrons from a source to an atom that is electron deficient, also known as the most positive atom present. Okay. How do we determine an atom is positive? Formal charge. What if there's no formal charge? Where's the partial charge in this structure? It's not written there. Is it actually there?
Yeah.
Yes. How do we know those partial charges are there? Polar bonds. We can identify a polar bond. How do we know we have a polar bond? Electronegativity. So when we started at the very beginning, I said we needed to be aware of electronegativity because this gets us where our electrons are located. When we know where the electrons are located, we can now say, hey, that electron can move. If I don't know any concept of electronegativity, all of this is rote memorization. Okay? This is why students freak out and say, oh, there's so much memorization. Because you didn't pay attention when we started the whole process. Okay? That's fine. I did it too. That's why I failed the first time through. I'm trying to make sure you don't. Okay? So we're saying the electrons move from the oxygen to the hydrogen. Can that hydrogen accept more electrons in its current form? There's our hydrogen chilling there. Can it accept electrons? So I'm hearing yeses and nos. For those of you saying no, why can it not accept more electrons? I'm hearing a statement that hydrogen already has 2 electrons. When does hydrogen have 2 electrons? I'll accept that, but we don't have a bond, so I don't accept that. When it's hydride. So we heard 2 answers when we have hydride and we have neutral. If we drew out neutral hydrogen, hydrogen has how many protons? 1 proton. If it is neutral, how many electrons does it have? 1 electron. Is that 1 electron 2? No. You might say, well, isn't this dumb? Why do I have to go all the way back to this? This is what we talked about on the very first day of class. I said, what makes up atoms? Protons and electrons. Like, oh, well, I understood all that from Gen Chem. You're now applying it. You have to hold that information and remember it. Muhammad suggested that hydrogen, when it is hydride, has 2 electrons. That's 1 proton plus 2 electrons. How do I know I'm looking at hydride? And don't tell me because it's a red hydrogen. That doesn't count. If we calculate formal charge is calculated by doing what? Valence electrons. How many electrons does hydrogen have in its valence? 1. Minus the number of bonds. Minus the number of electrons. And its charge becomes -1. How do we know we have hydride? We would see a lone pair, and we'd see a negative charge written next to it. Is hydride the same thing as H+? No. So how many electrons, because this goes all the way back to the initial question, how many electrons does H+ have?
0.
It must have 0. And we could do that by going through that same formal charge nonsense. Okay? Or we could go back to the very beginning of the semester where I said, remember we needed to memorize the charges of our common atoms and their bonding patterns so that we don't have to calculate the formal charge every single time? And you're like, yeah, I remember that. And I said, would you either need to memorize that or do tons and tons of Lewis structures?
Yeah, I remember that.
Thanks. This isn't a question that you should have said half the class saying it has 2 electrons. Okay? The H plus does not have 2 electrons. It has 0. Okay? And I'm not trying to say that you're wrong, horrible, and we all fail. I'm pointing out the deficiency. We need to fix that deficiency. Recognize where it is, adjust. Okay? So, to those that said the hydrogen could not accept electrons, can it accept electrons? Yes. Okay. It could accept 2 electrons because what is the valence shell for hydrogen? 2. So it can accept 2 electrons. Well, how many electrons is oxygen donating? 2. Okay. So the hydrogen doesn't exceed its octet by accepting those electrons. So is that arrow in and of itself fine? Yes. Do I need to add any more arrows? No. I'm done. That's it. I took the most reactive thing, H+, and I said, H+, stop being reactive. What made it reactive? The charge. What charge? Positive charge. How do you cancel the positive charge? Give it electrons. Oh, so we found a source of electrons, and we found a place that lacked them, and we matched them up. We matched them up using the curved arrow to show the flow of those electrons. How many curved arrows did we use? Exactly enough to satisfy our octets across the board. No more, no less. The result is I end up with this new structure. Right? Notice what changed. Yes, we have hydrogen attached. We have a positive charge on the oxygen, yes. We have 1 set of lone pairs on the oxygen. What happened to the other lone pair? It's now that bond. So recognizing how our notation changes that structure is what we're trying to focus on. Okay? So far, so good? Okay, so let's clean that up. This was chapter 7. And because we all raised our hand and said that we watched the video, or at least read chapter 7, you would be like, oh, I totally now know what the next question would be. Which would be?
What's the next arrow?
Next arrow is not a bad idea. Label the type of mechanistic step. It's an acid-base step. How do we know it's an acid-base? It's accepting a proton. We're looking at the transfer of a hydrogen ion from one place to another. That's an acid-base step. Okay? So now let's add the wrinkle that Nolan was suggesting we now do. We need more curved arrows. Okay? I'm going to make it a step harder. I'll accept that. That will now be the only information I give you. What is wrong with that structure? There's a positive charge on the oxygen. So we identify the most reactive thing and we say that needs to get fixed. Does oxygen want to be positive? Why not? It's the second most electronegative element on the periodic table. It does not want a positive charge. So what does it need? It needs electrons. So we'd say, okay, we just need to give it electrons. So I look over my arrow and I see that I wrote electrons. We got a couple things going to be problematic with that. So let's go through the things that are wrong with that. What's going to be the issue with just writing electrons in? I can't just write in what I want to have happen. Okay? There has to be something there. Okay? So that's issue number 1. Issue number 2. Let's say that I brought in those electrons and shared them with the oxygen. What's the issue with the oxygen? Already has its octet. I can't bring more electrons in because oxygen already has all the electrons it can possibly contain. Ooh. Third problem. Everything else has their octet, true, but it still doesn't get at our oxygen being positive. What's the issue with writing electrons?
Do you have electrons in solutions?
I would change your question from do you have electrons in solution to can you have electrons in solution?
Not free electrons.
Not free electrons. This was something you learned in Gen Chem. Don't get into the nuances. This was something you learned in Gen Chem. We looked at the transfer of electrons between atoms, and we referenced that type of reaction as a redox reaction. And when we balanced redox reactions, we could balance charges by adding in electrons. But electrons are such tiny, nasty little vicious things that can't exist on their own, which means we had to balance out half reactions. The only time we saw electrons in a reaction was for a half reaction. When does a half reaction ever occur? An acid base is a full reaction. In combination with another reaction showing electrons in what is known as a reduction and oxidation reaction. Why do we call them half reactions? Because we're only looking at the reduction, or we're only looking at the oxidation. This is a complete full reaction. Can I add electrons? No. Everything about that screams horribly wrong. Okay. Try something else. What's the problem? Oxygen is positive. Organic chemists are pessimists. Can never be positive. At least some people laughed. That wasn't too fake. How do I make oxygen not positive? I need to break a bond. Okay, I can't bring more electrons in. I can only use the electrons that are immediately accessible to the oxygen. Well, where are there electrons immediately accessible to the oxygen? In the bonds immediately around it. We have a red bond, a purple bond, and a blue bond. What happens if the oxygen took the electrons out of the red bond? Which means we would have to add an arrow down here. And just because a few people complained about this in office hours, we would then be looking at equilibrium. We all remember 152 with glorious fond memories of leaving the class. And yes, you're right. That is equilibrium, and we would then have to be concerned about it. Okay? That is a possibility. Does that take me forwards? No. In first semester, guess what? We really only worry about the things that take me forwards, which means, do I want to worry about the red arrow? No. Okay. Well, I also have a purple arrow. Way to guess where I was going with that. If we take those electrons from the bond and put them just on the oxygen, because remember, oxygen was positive. It needs those electrons. So we're showing where the electrons are moving. What would we produce? Same thing-ish as the last structure. No way to tell a difference between the new structure and the old one. Okay, so we're still carrying backwards. So is the purple arrow useful? No. So what should we do then?
Blue bond.
Let's take a look at the blue bond. So let's move those electrons. Stop lapping and give it away. What's the result? Did I do anything to the red bond? Did I do anything to the purple bond? Did I do anything to the lone pair that was on the oxygen? Right. Where did I take the electrons in that bond, according to my blue arrow? Took them from the bond and I placed them. Where did I place them? I placed them on the carbon. Can I draw that? Yeah. Is it correct? Okay, no. What I need to be considering is what are the repercussions of having done this? This is why mechanistic arrows are awesome. When you draw an arrow, what do you do? Exactly what the arrow tells you to do. Nothing else. I took those electrons and I put them on the carbon. That is the resulting structure. What is the result of that arrow pushing? Oxygen is still charged. What do you mean? Formal charge on oxygen is 6 minus 2 minus 2 gets me plus 2. Did I make the oxygen more or less happy? Less happy. What does that mean about that arrow? It's wrong. That's fine. Accept things being wrong, but you now need to fix them. So what do? Draw the arrow going the other way. The other way. I'm saying direction. I totally thought you were helping me. Ooh, interesting. What do you mean it doesn't look like the same? What's missing? Oh, I didn't draw the oxygen. Why did I not draw the oxygen?
You broke the bond and it's gone now. There's 2 compounds.
No, it's two.
It's 2 compounds. Okay, so let's fix that. We would draw it in like this, right? And we'd have the electrons, lone pair electrons on that oxygen, right? Why did we not show that? It's a really kind of bizarre, simple question, and you might not be happy with the answer.
You're just going to say because.
What was the name of this class?
Organic chemistry.
And organic chemistry looks at what compounds?
Carbon.
Carbon compounds. Does water have carbon in it? No. So what typically ends up happening? We ignore those structures. By we, I mean organic chemists as a whole. And unfortunately, in this case, I mean me too. Because I've done enough organic chemistry that what do? I have blinders on and I ignore the pieces that didn't have carbon in them. I will try my best to not do that. Because when you look at that, you might say, well, now I've destroyed matter. How did that happen? It's impossible. So I will try my best to always balance these out. Realize the convention is not to balance reactions.
So if we drew that with the L above it, would we get marked wrong because of the O's up there? Like the H2O's up there?
If you drew it exactly as it's shown here, spot on perfect. If you draw it like this, you're going to lose points. Okay. The results of that, the oxygen gained electrons. So its formal charge becomes 0. What happened to the carbon? I don't accept that it became positive. It's a little bit better. It lost electrons. There were electrons that it had access to in that bond, and where did those electrons go? Away from it, to the oxygen, which means the carbon now lost electrons. By losing a negative, we become positive. So far, so good? What type of reaction? Decomposition is not a bad one, but that's too Gen Chem. Heterolysis. Lysis meaning
Cutting.
cut. Hetero meaning different. The electrons are only going to one atom, not both. What if electrons had split and they each got an electron? That's now homolysis. We took the electrons and they went back to their parents. Okay? Because they're only going one direction, it's heterolysis. Is that a question? No? Yeah. Now what happens? What's wrong with this structure? Carbon has a positive charge. Does carbon want to be positive? No. So something has to happen. What's that something? It needs electrons. Do we have electrons from the outside available?
No.
Is there anything else written in there? No. Why is shaking his head no? Where do we have electrons available on the outside? I like your answer. There is some place that has electrons outside this. What is that? The oxygen has lone pair electrons. Could those electrons come back to the positive charge? Yes, which means it's also a reversible reaction. Right? We don't have another source of electrons that takes us forward, so we have to find electrons within the structure, and this is where things take a nasty curveball. We're going to take the electrons. I said takes. So if we did a double bond, what would we expect? Or if we took those electrons and we moved them to the bond, wow, in between, we would expect to see a double bond. Does that arrow end at the bond? No. Where is it ending? At the atom. So while it's a decent idea to think double bond, my arrow doesn't make sense for that. Add to that this result, I didn't make a double bond.
Oh, you just satisfied it to the charge.
So what happened? I took the electrons from that bond and just put them on the other carbon. And the hydrogen. So I'm taking a hydrogen with 2 electrons, which, Mohammed, is known as a hydride. And I'm changing the location of that hydride from one atom to another atom. I'm doing a shift of a hydride. So I'm doing a hydride shift. Where did that hydride start? At what atom number?
1, 2, 3.
I like 1. Where did it end? 2. It's known as a 1-2 hydride shift. Okay? We're doing what is known as a rearrangement. Rearrangements are obnoxious and tricky. Okay? They only occur because we're making something more stable. Okay? Because they are tricky, it makes their arrows look really uncomfortable too. Okay? Because if we use the arrow as it's typically designated, the arrow should actually be shown like this.
Why would that one?
Well, how is that different from this? You look at it and you go, oh, that's totally obvious. You're now racing through a test. Where did you go? Who knows? Exactly right. So when doing a rearrangement, okay, it is not a standard notation, but I've been told it's a British notation, which could easily be wrong. Make it look different. So we add a loop-de-loop, because we're now not doing a standard reaction, we're doing a rearrangement. And that can help call attention to that. Okay, again, it has to happen because we make a more stable product. Okay, well, we said our starting material was unstable because positive charge on the carbon, missing an octet. Is our product more stable? What makes it unstable? Positive charge on carbon. So which is more stable, a positive charge on a carbon or a positive charge on a carbon? They're the same, and yet I've heard a couple people say they're different. Why are they different? If we look at the difference between these, they both have 3 bonds. Okay? There's a 3rd bond out to a hydrogen out here. So they both have access to 6 electrons in the bonds. What's one step further out? Carbon, carbon, carbon versus carbon, carbon, hydrogen. Well, the carbons are the same. What's the difference between carbon and hydrogen? Before we get into electronegativity, we can move into size. I don't understand. What do you mean size? How is carbon different in size? Why is it different in size? I don't accept bigger. Someone mumbled something in here.
That has more protons?
More electrons. Electrons contribute size. Okay. Which I thought you said it first, and then you started saying the other things.
I said all of them.
Oh.
No, she said I did say electrons.
Oh, I only heard protons when I started making faces, I thought. So electrons. It has more electrons. What's going to stabilize a positive charge? Electrons. Which positive charge is more stable? The one near more electrons or the one near less?
More electrons.
The one near more. This rearrangement is a valid rearrangement because we make a more stable product. Okay? It's been painful, right? So let's simplify that out. Let's just take you all the way out. We've now added that bromide. What does that bromide bring in? Electrons. Okay? What does our original structure have? Positive charge. What should you do to stabilize a negative and a positive? Combine them. The other way? What do you mean the other way? I'm still combining the atoms.
You gotta move the electrons to the carbon.
Similar to nomenclature, just because you can understand what someone was trying to do does not make it correct. Okay? We must show the motion of the electrons. The bromide is our negative. It shares electrons with that carbon. Do we exceed octets on that carbon? No. Which means we don't need any more arrows. That would be the end of it. We have 2 questions. Why? And then I saw Henry.
Sorry, you're good. You're good.
Go for it.
Put in the bromide like arbitrarily, or is there what?
So deciding when and where these pieces come in is ultimately when we scaffold higher up. So at this point, really in chapter 7, it's just here it is, name this stuff. Okay? I made it more difficult because I started to remove and add things as we went through it. Okay? So chapter 7, you have all the pieces there. You start with the very beginning, and you just have to label things out. Is that what you're saying?
Why bromide instead of like chlorine or something like that?
Why bromide versus chloride versus iodide versus hydroxide? Okay? That's what we did here. Okay? So it's ultimately going to be given to you. This is what you're starting with. Okay? And we'll switch to that bromide question and again in just a second because we'll add another layer to it. The last thing we want to get through is what type of reaction here. I thought I heard someone saying addition doesn't work, unfortunately. It's coordination is how our textbook labels it. So we had one complete reaction, 4 distinct mechanistic steps with 4 different named types. By recognizing the type of reaction, you can then start to link these things together to make larger and more complex structures. Understanding the pieces is how you get there. Questions about what's up here before we go back to Wyatt's question? Okay. Here's Wyatt's question. Right. A little bit of edit. What reagent or reactant? What do I need to add to make this reaction occur? Okay. We just worked through the answer, so it's a little bit easier. Okay. But you could say, well, it needs to be HBr. Okay. Within that, you'd have to look at the reactants and products and say, well, what things changed? Well, what things did change? We lost the oxygen. Okay. Would I expect oxygen just be chilling out over here? Because if that's all that happened, we lost the oxygen with electrons. What can you tell me about this species? It's a base. And in particular, it's a strong base. What do strong bases do? React. This is a product. Should I expect to form a strong base? No. So if I just notice the only change is that bromide, and I say, well, the only thing I need is Br minus, well, then that says I form OH minus. Is OH minus a good thing to form? No, which means that reaction doesn't work. What do I need to make OH minus not a strong base? Hydrogen. So what do I have to add? The H. And I need HBr. It can't be, say, sodium bromide, because the sodium doesn't stabilize that piece out. So we've got lots of things, stacking and organization. They're all going back to the same basic fundamentals we've talked about through that very first unit. Okay? Questions about any of that?
Why can't we have
If it's sodium bromide, we form sodium hydroxide as a product. Is sodium hydroxide stable? No. We can't form strong bases or strong acids. Okay. I did intentionally pick this question and buried a little bit of information within it just to make it a little bit trickier. There's an extra caveat that we should theoretically need to be concerned about when running a reaction. Everything we've talked about so far is Chapter 7 and now Unit 1. Officially, Unit 2 is still in this question. Resonance is still, I would say, Unit 1. So spectroscopy. Do we see anything about IR, mass spec? No, that didn't really show up. If it's not spectroscopy, the other half of that test was chirality. Do we have to be concerned about chirality? Well, I don't see any wedges and dashes, so Mike's just full of crap and lying. What is special about that carbon? It's a chiral atom. Is chirality something that can have effect on our products? Yes. Is it going to affect this one? Why not? What was that? There's no chiral center in the product. So through the course of this reaction, even if we draw on chirality at the beginning, most of, oh my God, chirality, let's ignore it. Does it matter? No. Look at the product. Is there a chiral center in the product? No. Okay? So we have to be cognizant and thinking about it. That does not mean we will be constantly using it. And we only spent, when did class start? 11? 30? We only spent 50 minutes on one quiz. Okay? This is where we're trying to get to. Believe it or not, we've talked about acid and base in this. If we look at what happened, reactant to product, what changed? What's that? True. Let's look at the organic compound. What happened to it? Easier. What do you see in this reactant? An oxygen. What do you see in the product, or don't see in the organic product? No oxygen. So we lost an oxygen. Anything else happen? We gained a bromine. So we had an oxygen, and we did a switch, use fancier words, substitution. We did a substitution reaction. Acid-base substitution. We also have elimination, addition. Where am I? Acid-base substitution, elimination, addition, radical. 5 primary reactions. Okay. Within each of those, do we have different types of mechanisms? Yes. Notice within this substitution reaction, we didn't do just substitution steps. In fact, none of the mechanistic steps were called substitution. Okay. So we'll have the reactions that we have to name, and we also have the individual mechanistic steps. Figuring out how these pieces interact is what you need to pick up now for OChem. We've got our basics, we now scaffold. We need a minute? A little bit? Okay, I can take a minute. Okay? And those electrons will then move to some place that lacks them. Okay? Or lower in or higher in electronegativity. Okay? So do the wrong thing. That's good. But do it with the right mechanisms or the right bones. Process that out, see where the wrong path takes you. Okay? And it's recognizing those wrong paths now that will help you in second semester. Don't have to take second semester. Good luck. Okay? Process through all the right stuff you can and just hope for the best when it comes to the exam. Recognizing the wrong path is a good thing. So do the wrong thing. Shouldn't be a teacher telling you that. Okay? So, predict the products. Already. Expected because it's officially review. Okay? Or at least have come up with an answer. You may not be right, but have come up with an answer. So let's take a look at the first one. Come on, pen, work. I'm going to draw an answer. We'll actually only do the first one. We'll ignore the second one. The answer I'm going to draw, here we go. Or not. Let's try that again. Is that a valid answer? Yes, it is, but it's not right. I'll accept that one. Okay. What did HSO4 minus or HSO3 minus act as? If it acts as an acid, what is it going to do? Donate a proton. So that if I look at the product of HSO3 minus and find the most similar thing on the product side, HSO3 minus should have what? If it's acting as an acid. It should not have a hydrogen. It should have lost a hydrogen. Did HSO3 minus act as an acid in the reaction shown? No. What did it act as? A base. Okay? So it's acting as a base. What did NH3 minus then, or NH3 act as? Sorry. Had to have acted as an acid. Why are you saying that is bad? NH3 wants to act as a base more. Says what? What's that? There's getting at the right letters. Slightly wrong order. pKa. How many of you know the pKa of NH3? I don't accept your answer then. Try again. A number. Good point. So when we're looking at a reaction, we need to have some way to predict. In Gen Chem, you were told pKa's, and then you just had to run calculations off of them. In OChem, if you want to memorize pKa's, you can, and I do recommend that for some compounds, but not most. To predict which of these reactions, or which way this reaction should have occurred, we really need to look at the pKa's, because your other option, which is the one I believe you guys are suggesting I have drawn, would have been that one, right? So how would we decide which of those reactions is valid? That's a really hard question to ask. A question that OChem insists you answer. In Gen Chem, how would you decide? We established it. You look at the pKa's. Where are those pKa's coming from? From the Ka. How do we know the Ka? It's looking derived from our pH. We're looking at the concentration of H plus and our conjugate base and doing these big, long, drawn-out calculations. Okay? And we would then evaluate at each of those stages to try and decide. So let's take a look at the pKa's for some of these things. Let's take a look at the pKa for NH3. It is probably proven wrong later, but I'm going to guess 35. The pKa of H2SO3. Anybody know the name of that compound, out of curiosity? H2SO3. Say that again? Not sulfuric acid. Sulfurous acid. Which species is probably the stronger acid? Sulfurous acid or ammonia? Probably the one we called an acid. So if we go through and take a look at this, this is something like, and again, you can probably prove me wrong, but I think somewhere in the order of -1. Let's just say -1. What does that mean? Which is the stronger acid? H2SO3. How do you know that? Don't tell me because it's acid.
No, that has a lower value of pKa.
If you know the pKa, you can compare the pKa's. If this is the reaction drawn out, is it likely to form products? No, because we're looking at, that's a difference of 30 pKa's or a scale of 10. 300 times less acidic on the reactant side. Where's my reaction going to favor? The reactant side. This reaction doesn't make any sense. What happens if we scale down to the other one? We've got a pKa of HSO3 minus, and this is going to be a fun week. I think I'm just losing my voice. I didn't use it anyway, right? Where am I? HSO3 minus, probably a pKa of about 4, pKa of NH4, about 9. Where would we expect our reaction to favor? Favor our products because the pKa of NH4 is higher, which means it is less acidic. That reaction seems to make more sense. So we could go through and use pKa's. Right? What if we don't have the pKa's? How can we start to predict things? I can use electronegativity. Let's take a look at that top equation, because I think that top equation is easier to work with. What's the most reactive thing on the left-hand side of the equation? HSO3. Why? Minus charge. Where's that minus charge being held? What atom? On the oxygen. What is the structure of that compound? How would we figure that out? We draw out our Lewis structure. And because I picked one that was conveniently not super easy, I'm not sure I can draw it off the top of my head. But we'll just guess, say this is it. Probably pretty close. What's the most reactive thing on the right-hand side? NH2. Why are you saying the NH2? Negative charge. Which atom is holding the negative charge? We compare the sides of the reaction, decide which of those is more reactive. The side that's more reactive, I want to avoid. Okay? I have a negative oxygen as the most reactive atom versus negative nitrogen. Which of those is more stable? Oxygen. And Sam, you should be able to answer this. Why is that oxygen more stable? Oxygen is the second most electronegative atom, which would suggest it can hold a negative charge better than the nitrogen. We don't need pKa's to do these predictions. We can come up with generalizations from electronegativity. Okay? So we can make quick general observations. Those observations will allow us to predict. So when I made reference to electronegativity and resonance, it's important for this reason. I can now predict reactions without having to do all of the calculations you did in 152. For those of you that liked those calculations, you can go back and take it again. I'm fine with that. But I don't want to teach it. Okay? Good, because you didn't want to take it with me anyway, right? Acids and base definitions. And the acid and base definitions that you likely worked with in Gen Chem were Arrhenius. The Arrhenius definitions were based off of observations when he added these things to water. Okay? Already we should be screaming, that's a problem for OChem, because water's not organic. So we've got issues with our definition already. Okay? He said acids were H plus donors, so we noticed the H plus concentration went up, and bases, the hydroxide concentration went up. The issue with this is it's too narrow a definition. So for the sake of organic chemistry, it is completely and utterly useless. Okay? So we need a new definition. The new definition we use comes down to Bronsted-Lowry. And Bronsted-Lowry expanded the definitions a little bit because what they looked at and said, well, let's just look at H+. OH minus, when it's acting as a base, is doing what? What is it reacting with?
Hydrogen?
Protons, H+. So instead of coming up with two things with different definitions, because we know they're related, tie them to each other. And we end up with our Bronsted-Lowry definition, which apparently has some font issues within Word. Right? O with the dots. So we get H+ donors are acids, H+ acceptors are bases. Right? H pluses tend to be referred to as protons. Okay, why? What is H+? Well, it's a hydrogen atom. Hydrogen has a proton and an electron. What happens when we make it H+? We get rid of the electron and all we have left is a proton. This does not mean we're doing nuclear chemistry. Okay? We're just saying we have an H+ floating out there. It's still called a hydrogen atom because that proton is not in another nucleus. So if we took a look at some practice, I'll give you a minute. Name them. Acids, bases, or neither. First one is acid. How do you know it's an acid? Hydrochloric acid. I accept that. Use the easy answer if you got it. Next one. Base. Why is that a base? Sodium hydroxide is the definition of a base. That was our Arrhenius definition. Okay? Let's take it a step further than that, because that doesn't quite fit our Bronsted-Lowry definition. That splits as an ion, we get a negative oxygen. What can stabilize that negative oxygen? A proton. So that OH, or that negative oxygen, would accept a proton, thereby making it a base. Next one. Next one. Base. Again, we can cleave that sodium. We get C2H3O2 minus. Right? And that negative charge can pick up a hydrogen. NaCl. Should really be neither. The sodium can't really react to pick up OH minus, because if it picks up OH minus, it becomes sodium hydroxide, which is strong base. So that's bad. The Cl can't really pick up a hydrogen because then it becomes a strong acid, also not allowed to form. CH4. NH3. Ooh, wow, things started to get tricky real fast, didn't they? That's our base. How do we know NH3 is a base? It's not NH3 minus, ignore that. What lone pairs? The lone pairs on nitrogen that were implied? Yeah, those lone pairs. What did we need to accept a hydrogen? Electrons. What does the nitrogen have? Electrons. What did the hydroxide have? Electrons. The acetate? Electrons. Right? If we have electrons, we have the potential for a base. Not always, because what does the chloride have? Oh, shoot. It has electrons. That didn't quite pan out. But we're looking for some kind of electrons. There are better sources than others. The last one. The first person I heard shout out said acid. The second person also said base. Guess what? It can act as both. Why can it act as both? It has the hydrogen connected to that oxygen. Oxygen being more electronegative and take the electrons away from hydrogen, and we now have H+. We also have a base because, and I want to hear this answer, and I don't want to hear that answer, so if anybody heard him, don't say that. Why is it a base? Thank you. Unfortunately, you're wrong, but I wanted to hear that. Okay. The answer I heard was hydroxide. Because this is what Gen Chem does. says this is OH. OH is hydroxide. Nonsense. It is not. What is OH? I don't know. If I put that OH next to metal, what happens? I have an ionic bond. The oxygen steals the electrons from the sodium, and I have hydroxide. Now I have a base. And now I have hydroxide. What if I bond that oxygen to something other than a metal? Well, now they share electrons. It's not hydroxide anymore. It's technically hydroxyl. If it was a carbon, we'd call it an alcohol. This is an alcohol. What makes the oxygen a base? And I actually gave the hint away there. That compound is a base not because it's hydroxide, but because it has an oxygen. More importantly, what does that oxygen have? Lone pair electrons. It is the lone pair electrons on that oxygen that are acting as the base, not that we have hydroxide. Okay? So we're looking for patterns, trying to come up with ways to label. If we go through and use the Arrhenius definition, 7 doesn't make sense. If we use the Arrhenius definition, 8 doesn't make sense. That's why Bronsted and Lowry expanded the definition outwards. Okay? That definition works out great in a lot of cases. Say this first example here. What changed? Look at that first reaction. What changed? H3O plus lost a hydrogen, so that would be acting as an acid, a proton donor. What else happened? The other oxygen accepted that hydrogen, so it would be a base. Just because I love color coding, let's go ahead and do that. Would that be a good mechanistic arrow? What do you mean no? Hydrogen would have exceeded its octet. That's a problem. Is the arrow wrong? No, the mechanistic step I've shown is wrong because the mechanistic step hasn't shown everything that needs to happen. We know we have the products on the right. We have to add curved arrows to make sure that we get the products on the right. And we do that, Jenna, by taking the electrons in the red bond and moving them to the oxygen. Now we've shown the correct mechanistic step. The overall process, we transferred electrons between atoms. If we look at the atomic picture, we transferred a hydrogen from one source to another. Simple transfer of a hydrogen, Bronsted-Lowry all the way. What happened in the bottom reaction? So ignore all the stuff in the middle. Almost all the stuff in the middle. We still need that. Could say a substitution reaction. Is that acid-base? Did we transfer a proton? What proton did we transfer? Okay. We broke a bond here. We made a bond over here. There's no hydrogen transfer here. This doesn't fit Bronsted-Lowry's definition. And when we were coming up with these definitions were meant to apply universally to absolutely every reaction out there. The Arrhenius definition failed, so we did Bronsted-Lowry. That expanded the subset of our bases. What happens when we look at other reactions? Does our Bronsted-Lowry work? No. So if it doesn't work, what do? We make a new one. The new one was developed by a man by the name of Lewis. He went through and said this transfer of atoms is irrelevant. Right? If we look at relationships between people, it's not that we have people. Right? I'm not in a relationship in that sense of the word with all of you. Right? That doesn't make sense. Right? What makes that a relationship? We need an appropriate distance between them. Okay? But just because I stand next to Nick the same distance I stand from my wife, does that mean I have the same relationship with Nick as I have with my wife? No. What else is going on? There's a transfer of some invisible material. Okay? Hearts, love, character. That invisible material in the case of chemistry is electrons. That's Lewis's definition. He expanded that definition to now say we have electrons that are now moving between. Okay? So we still have acids and bases. You might say, oh, that's a new definition I have to remember. It's the exact same. An acid was a proton donor, H+. What does H+ need to do if we look at the electrons? It needs to accept electrons, making it a Lewis acid. It's the same definition. We're just shifting our focus to the electrons. So that when I now go through and down, look at this last equation, what did the cyanide do? It shared electrons. It lost electrons. So it was an electron donor, making it a Lewis base. What did the other structure do? It accepted those electrons, so it's now a Lewis acid. So it's applying those definitions. Where does this become problematic? Well, let's go up to the previous equation. What did our base do in the case of the Bronsted-Lowry? It accepted a hydrogen by doing what? Sharing electrons. Which then means it's a Lewis base. Am I doing the same fundamental chemistry between those? Kind of, sort of, but one's looking at the specific transfer of a hydrogen. So I could refer to all reactions according to the Lewis definition, but that now narrows things or expands things to apply to everything. And if I want to now say acid and base and mean that we're doing the transfer of a proton, I want to make sure that when I say acid and base, you know it's a transfer of a proton. It's a labeling issue. So I don't want to call things Lewis acids and bases because that definition is too narrow. So I'll add a new definition into this. And it's not just me, this is organic chemistry. You'll introduce the idea of electrophiles and nucleophiles. They are the same inherent thing as acids and bases. The one difference, you're not transferring hydrogens. That's it. Okay? And with that, we're well done.